Okay, welcome back to part 4 of our Introduction to Modeling of Ground Heat Exchangers. In this part, we're going to do a numerical example and with a little bit of computer code. So the example where we're going to use the line source approach with temporal superposition. In other words, the heat input's going to change over time. Right, so to start with a relatively simple example, I wanted to use a short example, and I will lecture separately on thermal response testing, but thermal response tests are used to make measurements in situ of the thermal conductivity of the ground surrounding a borehole. Right, and what's done is we impose a heat pulse on a U tube, right, so we circulate warm water. There's a long history to this. It'll take more than I don't plan to discuss it all here, right? And then we use the temperature response to estimate the thermal conductivity. And I took a test done by my colleague, Dr. Marvin Smith, in 1999. I pulled up the results. They were the first ones I found when I was looking, and they're 1-minute results. And so I converted those to hourly values because I don't want to have 1-minute time steps in our simulation. So, and it's about a 50-hour test, so we have 50 hourly values. And for analyzing a thermal response test, one approach is to use parameter estimation. Then we'd automatically adjust say the ground conductivity and the borehole resistance to give the best fit. Okay, I'm not doing that here. There's no outer shell. We simply what we have is a simulation. And we can look at the effects of changing the ground conductivity and borehole resistance. And so what I did is use that information to sort of roughly estimate what the ground conductivity is likely to be. So if you look at the results, and I'm going to show you some measurements first. So first of all, we try to maintain a reasonably constant power input. Right? And there is another way to analyze these tests related to the line source. If we plot this on the mean fluid temperature versus the log of time, that it should form a straight line that once we overcome the transient conditions in the borehole. And if we take the slope of that, that's proportional to the conductivity. So that's another way to analyze the test. So we try to but for that you really must have a constant heat input. And this one's test is actually pretty good. You see it's a bit higher early on, around 10 to 15 hours, and it drops off, comes back up a little bit again. It varies, but it's pretty well maintained. So if we look at the temperatures, we've got the mean fluid temperature, this middle curve. The temperature here exiting the borehole, right? So we're putting warm water in, that's the input here, and then it comes back out somewhat cooler, right? So it's fairly smooth curve. It's pretty good test quality. You'll see that the flow rate varied, but if you look at the scale, right, for the most part, it's in a pretty narrow band, maybe maximum 0.222. Most everything, most minutes, if you think about 50 hours or something like 3,000 minutes, only a handful get much below 0.212, so it's a pretty narrow band. It's pretty well controlled. And we're going to do a simulation. I'll pull it up live, but I've got a few slides that just sort of show what it is we're doing. We read the simulation parameters from a worksheet called Sim. Right, and so I have undisturbed ground temperature, and I used that. Before we started the heater, he circulated some fluid, and I took the mean of the temperatures over about an 8 or 9 minute period to estimate the undisturbed ground temperature. The conductivity, this is actually my sort of best estimate. I mean, we will play around with it. Rho CP, I just took a typical value for the rho CP of the ground. The borehole resistance, again, I adjusted that to meet the conditions. I didn't actually look to see for sure the depth, so it's possible I don't have the right depth here. if you don't have the right depth, you can still get an answer that looks perfectly good. It just won't be right. So, and the borehole radius also, I didn't check that either. It should be somewhere around 0.07. So I'm not going to say what kind of grout, and so I know what kind of grout is in the borehole. I won't say, but we'll just assume these numbers are right for purposes of our example. All right, and then what I've done is, this is all the data that was provided or measured. I've converted it to hourly values, and literally what I've done is I've taken the average over the hour and used that value, but I've used the instantaneous value of the measured exiting water temperature and entering water temperature. By the way, he used a different convention, so if these seem mixed up, these are okay. This is, sorry, I guess I fixed it here. The exiting water temperature, this is coming back from the borehole, so it's exiting the borehole. His original data said he used exiting and entering as if it was from the test unit. So you can see about a 3 degrees C delta T across the borehole there. Okay, so these I'm only using for comparison purposes. For the actual inputs to the simulation, I'm using the power, so it's changing some. And I'm using the flow rate, and I've converted this from liters per second. I estimated the density of the water based on I think on the mean fluid temperature. And so I've got a mass flow rate at the end of each hour, not at the, not averaged over the hour, but just at the end of the hour. Okay, and this is the actual code. It's actually 2 pages. This is all the VBA code. Well, it's all the VBA code to do the simulation. I wrote another short subroutine that post-processed the 1-minute data into hourly data. So it's, and this is not set up as some kind of general purpose code. It's just set up to do this case. We had fixed intervals. All the data was measured on 1 minute, and then I took it every 60 minutes, or in the case of the power, I averaged it. Let's see. So I read the parameters from the parameter section: the undisturbed ground temperature, or the far field temperature, conductivity, rho CP for the ground. I think that's rho CP for the ground. We'll take a look. Yeah, alpha, the thermal diffusivity, is the conductivity divided by rho CP. The borehole resistance, the depth, and the borehole radius are all computed. We have some intermediate values. Well, we need a value of pi, and FPK, 4 times pi k, alpha of the diffusivity of the thermal diffusivity of the ground, K over rho CP. And then this oddly named parameter, which is something like radius of borehole squared over 4 alpha of soil. Yeah, it's probably going to be hard to remember, but that's what I'm using. Set up to do 50 intervals. We have a little bit over 50 hours, so it's like 50.3 hours, so we just stopped at 50. So I read the hourly values from the sim worksheet, and I divide the Q. We have watts, and I want watts per meter, so I divide by depth and read the mass flow rate. Those are the inputs. Then in the second page, now we do our simulation. Right? And we do this for each of the intervals from 1 to 50, and for each one we have to do our own new superposition. And there are different ways to do this, but we've just kept this simple. I'm just summing up for every interval, for every time that we want to estimate at. We have to superimpose all the pulses before that. Right? So that's what this loop is doing. So the outer loop does each interval. The inner loop does for each interval. It sums up all the past history effects. So I've got I've got a time for each interval. So if you say the first interval goes, or the very first pulse applies over the whole time period up to the nth interval, right? And so we get this, calculate the time, calculate the pulse. There's the Q over, or Qi minus Qi minus 1. The argument to the exponential integral, the e sub 1, the argument is this. It's the Borel radius squared divided by 4 alpha times the, in the denominator 4 alpha times this time, right? This is all constant, it doesn't change, so I just divide it by the time duration here. Calculate using this simple function, right? And this is this simplest function. I see I've got an error here. It says this function implements the expansion given in Abramowitz and Stegun. That's not correct. I did implement a function, and I changed it. So I'll try to remember to take that out of the comments there. This is just the very simplest form, right, which is ln of alpha 4 alpha t over rb squared, or 1 over z. So it's the natural log of that minus the Euler's constant gamma. Okay, so we calculate that, so we sum up the effect of each pulse. So dt is of 1 pulse, and then we sum these up. When we've summed them all up, we're ready to find the temperature. So this is that total temperature change at the borehole wall. Q times RB is the temperature difference from the borehole wall to the fluid. And the UGT, undisturbed ground temperature, is the same as the far field temperature. And then the specific heat of the fluid, CPF, I get that I use the mean temperature to compute that. And then the exiting fluid temperature is, again, the change of the borehole wall plus the change due to the resistance across the borehole plus the undisturbed ground temperature. Okay, and then this delta T over 2, that's this part here, minus Q of n times the depth over 2m dot CPF. Right, here our Q is, we computed to watts per meter already, so we need to get it back to the total watts. So we multiply by the depth, or I think in the equation I called this L, QL. Okay, and then we write this back to the spreadsheet. Okay, so that's what it looks like. Let's actually pull it up and bring it over here. Fit this into the window if I can. Okay, so I'll upload the spreadsheet. So there's the raw data here, and you see some negative times. Those were before the heater was turned on. So if you saw, I used undisturbed ground temperature 17.53. It's the average of the entering and exit after we started to circulate the fluid, but before the heater turned on. And yeah, so that's all the minutely data. And then I have there's another module called processing. This is the subroutine that took the minutely data and converted it to hourly. And as an aside, I realized that one thing I did that wasn't maybe exactly consistent is for Q, I took the average for the hour, which is fine, but possibly when I calculated the delta T, I should have maybe used the Q for that time rather than the average for the hour. It would make very little difference, I don't think, since we had a fairly even power distribution. But I tried to do everything else that was related to the borehole, where we assumed quasi-steady with the instantaneous value at that point. Okay, so that was the routine that did the processing. And then the simulation routine, I've already shown you this. And we're going to take actually both of these out. And we don't need this other comment here. I had this, I think I had a 10th order expansion. Actually, that's what I started with before I decided just to drop all that. Okay, so that's saved. Okay, so, and then I put a button on the spreadsheet. There's the plots, TRT, simulation. And when I started, I didn't have a good idea of what the ground conductivity was. Now it's, I'll just say that 2.8 and an RB of 0.18 give us a pretty good idea. And I've got 3 plots. Let me see if I can arrange these so they fit a little better on the page, or on the screen, I should say. Well, we may just have to adjust things a little bit. So this one, I've just got a plot of the measured mean temperature, fluid temperature. That's the gray, and the blue is the simulation. And this plot is the same, but you see I've plotted on a log plot the log time here. And the reason I did that is when we start and we don't know, so if we just say put a conductivity of 2 here, right, and we simulate it, you see the slope here is quite a bit different. And I mentioned to you that for thermal response tests, there's an analytical procedure where you find the slope and you use that, a slope on the log plot that is proportional to the conductivity. The problem is if you look closely, and maybe we may want to expand this plot a little bit to see this better. See this gray? There's actually 2 different, there's an early time slope, right? This is 10 hours, so presumably what's going on here is due to the borehole, but then, so it sort of settles down, but you see even then there's a slope there, then there's a change, and maybe another slope there. So that's one of the reasons to use parameter estimation if there's, but it may not help us all that much. We're not using parameter estimation here, we're just guessing. So if you say go 2.5, right, you see, oh, well, it does actually match the slope there pretty well. The other thing we don't know at the beginning is the borehole resistance. So if I put it a lot smaller, 0.1, oh, then it says, oh, the temperature wouldn't have risen anywhere near as much. So the approach I used was knowing that if I got the slope to match approximately, basically I just refined these guesses by human insight. Right? So this separation here tells me that the borehole resistance is off pretty far. So if we go to 0.2, right, it's like, oh, we've gone too far. And 0.18, we simulate, we do a reasonably good job here. Now, recall 2.8 is what I had settled on earlier. Right? This is not perfect. We don't expect it to be perfect in this region here. right? Where we're not so much seeing the effects of the transient heat transfer inside the borehole. But in here, we expect to settle down, and we sort of have. It's a little bit hard to be absolutely sure. And if I was really trying to analyze this, I would probably use parameter estimation to sort of come up with the best estimate of conductivity and borehole resistance. But the point of this really isn't how to analyze a thermal response test, but rather how to do a simple simulation. So we've taken the line source, the theory, all the way up to the point where it's predicting the fluid temperatures in and out of the borehole. You see we get reasonably good match for the mean fluid temperature. If you look at the exiting fluid temperature, well, we're reasonably close. We're off by 0.2, 0.3 degrees. We might be able to do better, but I would say in general, you shouldn't expect that your simulations of ground heat exchangers are really going to be much better than this. Okay, so let's go back then, right? So we've, again, adjusting the inputs in a way is the whole point of the TRT. There's a lot more to be said about thermal response tests. I think there could probably be a whole, several lectures on thermal response tests, certainly. If you're interested in the meantime, my recommendation is to read this paper by myself and my colleague Singhil Jalin from Sweden. We both started working on this in the mid-1990s, and this is sort of a historical review paper. Okay, so far we've looked at a single borehole, but in fact many ground heat exchangers have more than one borehole. Certainly, I'd say in the U.S., the lion's share will have more than one borehole. In Sweden, it's common for houses to just use one borehole, although it might be 150 meters deep or more. Right? So you can more easily drill deeper in hot rocks. So if you have, say, two boreholes, this is only two, but we might have 100 or 500 boreholes. If I've just sort of put two in a line, they're 5 meters apart, and you can see after some time, I don't remember how long a time this was, but the first borehole by itself would have this sort of green curve. That's what it would be, the ground around it would be seeing, right? And if we just had the borehole 2, we'd have this red curve here, right? But in fact, we're going to have to superimpose both of these. By the way, we can do this because the heat conduction differential equation with Fourier's law is a linear differential equation. And that's what allows us to do this superposition and have it be extremely accurate. Right? So, but if you add the two curves together, then you get the black, right? And I'm sorry, I don't remember what the time interval was, but what you can see, basically we keep putting heat in the ground. And instead of being the 14 degrees at the borehole that we expect, it's actually more like 16 degrees due to the influence in both cases of the other borehole. Well, that'll come up in a future lecture topic. So I try to think about what else we might discuss related to modeling of ground heat exchangers. First of all, we often want to use non-uniform time steps. It's important to save computational time. We also, so far, you saw for 50 hours, 50 steps, it worked very fast for us to just sum up. By the 50th hour, we were summing up 50 responses. Right? But if we do a 20-year simulation, by the last hour, we're going to be summing up something like 170,000 individual hourly responses. And the speed would get quite low. So we've developed some methods for aggregating the loads, and that requires treating non-uniform time steps. Typically, we don't use the line source for doing this, at least not the infinite line source. And we usually use some response factors, and when they're computed, we usually non-dimensionalize them, and they're called G functions. We may discuss how to compute G functions and the boundary schemes used to compute G functions, and thermal response tests. They're all related to what we talked about today, but we can't cover everything at once. Okay, the last few slides here are just the references. So many of the papers referenced in the following slides, the ones authored that I authored, many of them are available at our website, our research group website. I mentioned GLHE Pro, EED, and Energy Plus as of 2020. This is the website for each one of these. As two overview documents, my colleague Michelle Bernier and I wrote a paper on design methods for borehole ground heat exchangers, and that covers some of this material. It's a little bit broader since it's more focused on methods for design, so it's not all about simulation, but it does cover simulation. It was edited by Simon Reese. And the other on the thermal response test, I'd recommend this paper, really explain how it got started, and I believe it does a good job of explaining the methodologies and later developments and so on. And then the references themselves are here. Some of these are available online. I didn't try, like actually this Handbook of Mathematical Functions by Abramowitz and Stegan with the Gauci and Cahill chapter. That's actually, I found that online. Most of the theses are available online, and then some of the papers are available on our website. So that's it for now. Thanks.